Section 8. So now it's alternating currents. Actually, without ever using the word, I'd already started talking some about alternating currents at the end of section 7. Those electrical oscillations you have in an LC circuit, those are alternating currents. But now, instead of just having an isolated capacitor and coil hooked up to each other, yeah, let's talk about like your vacuum cleaner plugged into an outlet or something like that. But first, and maybe I should have even done this last week, let's make sure everybody's up to speed on their trigonometry, because you had that function Q max cosine of omega t plus phi. So what exactly is a cosine, among other things? Well, trigonometry deals with right triangles, such as the one in front of you there. A right triangle is one that contains a 90-degree angle. The two sides of the triangle that are perpendicular to each other, the two sides that make the 90-degree angle, are called the triangle's legs, and the side that's across from the legs is called the hypotenuse. If you single out one of the non-90-degree angles for special attention, like the one that's been labeled with the Greek letter theta here, then you can distinguish between the two legs. The leg which is part of the angle theta is called the adjacent leg, and the one that's over on the other side of the triangle from theta is the opposite leg. Trig functions are ratios between the lengths of the sides. Sine is opposite over hypotenuse and so forth, like it says there in front of you. And this is written on your formula sheet somewhere too. So if you can't, you're like, oh, I can never remember. Is tangent opposite over adjacent, or is it adjacent over opposite? It's on the formula sheet, look it up. So let's say you wanted to determine the tangent of 30 degrees. Now, this would be a rather crude way of doing it, but it illustrates what the tangent means. You could get out a sheet of paper and a protractor and a pencil and a ruler. And the first thing you do is, using your protractor, you draw a 30-degree angle. And then maybe you make the one side of the triangle 2 inches long, okay? The hypotenuse, 2 inches long. Or maybe you don't. It doesn't matter. The sides are going to come out with the same ratios. If you make the hypotenuse 4 inches long, then the opposite side will be 2 inches long instead of 1, and you'll still have the same ratio in between them. So you draw a right triangle, or you draw a 30-degree angle, and then over on the other side, you make a 90-degree angle to finish off a right triangle, and then you start measuring the sides. And let's say you get the numbers that are shown here. So then you divide, okay? You want to know the tangent. It's the length of the opposite side divided by the length of the adjacent side. 1 divided by 1.73, and you get 0.577. And, try it for yourself if you feel like it, and you should get something fairly close to what you get off of a calculator. The graph of a sine function looks like this, kind of wavy. A cosine is basically the same thing as a sine, except it's been shifted a quarter of a cycle to the left, so it begins at a peak instead of beginning at 0 like the sine does. And the other thing about right triangles that comes up fairly often, can be useful to know, is the Pythagorean theorem. C squared, well, whatever letters you want to give them. The square of the hypotenuse equals the square of the one leg plus the square of the other leg. Okay. So That's like a 5-minute review of trigonometry. Well, not everything in trigonometry. They don't manage to make it a full year course in high school with just that, but that's high points. Okay, so an alternating current. If you plug in your vacuum cleaner, because house current is AC, okay? The current in the cord leading to the vacuum cleaner is not steady like you'd get from a battery. Instead, it varies back and forth like a sine wave. See, we're using that trigonometry already. The current I as a function of time t is a sine wave, just like out of a trigonometry book. The voltage as a function of time is also a sine wave, more or less. The current and the voltage do not necessarily rise and fall together. They might not, depends on what's in the circuit. So remember that thing about a phase angle that at the end of section 7, I said, oh, you don't really need to worry about that. Well, you didn't need to worry about it then. But in these two graphs you have in front of you here for current and for voltage, there is a phase difference between them, okay? So whereas the current just is proportional to the sine of omega t, the voltage is proportional to the sine of omega t plus the phase angle, phi. And the graph shows how that the value of that phase angle shifts your sine wave to the right or to the left along the horizontal axis of the graph. If the phase angle actually was 90 degrees, it would turn your sine into a cosine, except, of course, we don't want to be using degrees, we want to be using radians, remember. So omega means the same thing it did in section 7, omega equals 2 pi f. And so those are the graphs and the equations that go with them for alternating currents and alternating voltages. So down there at the bottom of the page, it says, what does 1 amp of alternating current mean? Well, here's what it doesn't mean, first of all. I think this continues on the next page. Let's see. No, I get into power over there. Well, first of all, it does not mean the average current, okay? I mean, with DC, it's simple. If you got an amp in the wire, that means there's 1 amp flowing in the wire, you know? Current coming out of a battery is nice and steady and simple. Well, here you've got this current that's constantly changing. So how do you put a specific number to something that's constantly changing? Well, first of all, it's not the average. If you think about it, look at the graph, the average current is 0. You've got the top half of the wave there where the current is positive, and then you got the bottom half of the wave where the current is negative, and it's just as negative for just as much time as it was positive in the other half of the cycle. And so the average averages out to 0. And another thing that the 1 amp is not is it's not the peak value, okay? The current where the graph tops out is not 1 amp. It would be a little over 1.4 amps actually. So what is it? Well, we'll get a little more specific about that on the next page, but the basic idea is 1 amp is the effective current, okay? Some of the time the current is more than 1 amp, some of the time the current is less than 1 amp, but it averages out, not average in the sense of just a regular mean, but in the sense of this alternating current would make your toast get just as brown in the same amount of time as if you had a steady DC current of 1 amp, okay? So this constantly changing current you have has the same effect as a steady 1 amp would. Or the way it's phrased here, it would deliver the same power, which is kind of what I meant by it would make your toast get just as brown in the same amount of time. So power, if it's going to be delivering the same amount of power, power is equal to I squared R from several weeks ago. And it's also equal to V squared over R if you want to calculate it from the voltage instead of the current. So to calculate the average power delivered by an alternating current, we're not so much interested in the average values of I or of V, which, as I just said, those are 0. What you're actually interested in is the average value of I squared, or the average value of V squared, because those are the things that are proportional to the power, and the power is the thing that's proportional to how brown your toast is. Well, you see, if you go squaring, and maybe I should put it up on the blackboard for a moment here. Gotta find just the right spot for the camera. I guess that'll do. Sine wave looks like that. Positive, negative, positive, negative, positive, negative, and averages out to 0. But if you square it, sine squared, I should have made that line up with that. I wasn't being very careful when I drew it, but you take a negative number and you square it, and it's positive, okay? So sine squared is always positive. And so when you average that, you get something which is not 0. So back to the other thing. The average values of, I should have pointed out, I suppose, that it's a nice symmetrical curve when I still had that curve in front of you that, well, anyhow, the sign goes back and forth between plus and minus 1. Therefore, sine squared goes back and forth between 0 and 1. And this is one of those it can be shown things, but it can be shown that the average is right in the middle. The average value of sine squared, or for that matter, cosine squared, is 1/2. So anyhow, what did I write here? Average power is equal to the average value of I squared times R. Okay, since power is I squared R, average power is I squared average times R. And as I just got done saying, the average value of I squared is half of the peak value. Okay, sine squared maxes out at 1. The average of sine squared is 1/2. So the power is equal to sine squared, or the average, the power is equal to sine squared times I max. And so I max squared over 2 times R. That is the average power. And so the square of the effective current would be I max squared over 2, but nobody wants to go around talking about square amps all the time. So you take the square root of it. This is another type of average, okay? The word average usually means that you calculate the mean. You add the numbers together and then divide by how many numbers there were. What we're using here is another kind of average called a root mean square, where it's a little bit more elaborate. You square the numbers, average the squares, and then take the square root again. And that's what RMS stands for here. Root mean squared current, root mean squared voltage. This is the effective current and the effective voltage. The amps and the volts that would deliver the same power if it was just steady amps and steady volts. Okay, so maybe I got a little long-winded there. But the point is that the effective current equals the peak current divided by the square root of 2. So if you're, back to the original question up at the, well, still can see it there near the top of your screen. What does 1 amp AC mean? Well, you've got a graph that goes back and forth between, see, the square root of 2 is 1.41. You've got a graph that goes back and forth between plus 1.4 and minus 1.4 over and over again. That will deliver the same power as a steady 1 amp would. So RMS current versus maximum current, or peak current if you want to call it that. Same sort of thing with voltage. Root mean squared current is defined in a way that makes the average power delivered to a resistor equal to I squared times R if you use the RMS current, okay? Toasters are basically resistors, hair dryers are basically resistors, anything like that. AC meters read RMS values. This is something people have attended. I mean, you go into a physics book and there's a lot of stuff about the maximum voltage or the maximum current because they draw a lot of graphs, and the amplitude, the maximum, is easy to read off of a graph. But outside of a physics book, when you're talking about the real world, if you go over to Home Depot and you buy a box of wire, you're going to, do a little wiring project, assuming you know what you're doing, of course. If it's 14 gauge wire is good for 15 amps. 12 gauge wire is good for 20 amps. And those are root mean squared, not the peak, okay? If you go over there and you buy a circuit breaker, if it's a 15 amp circuit breaker, that breaker will trip when the RMS current is 50. Meters read RMS. Basically, all anybody ever talks about when it's practical electricity is the effective voltage and the effective current. So when you read 1 amp or 120 volts off of a meter, keep in mind that that's not the maximum, okay? Ordinary household outlet, 120 volts. As the voltage varies back and forth, it's going back and forth between about plus 170 and minus 170. It's that square root of 2 thing again. Well, anyhow, I've babbled about that for long enough, I think. So there's a problem for you to do. Basically, what it's asking you to do is take the numbers given in the question and back, let's see, where was that? Oh, somewhere right around here. We have a formula for voltage as a function of time. You need to come up with numbers to stick in there for Vmax and omega. And so you get a formula for voltage as a function of time in this particular outlet. By the way, when you say house current is 120 volts, they don't have to be too particular about that. Most electrical equipment sold in this country is designed to run on anywhere from about 105 to 125 volts at least, something like that. So, you know, if you've got 122 or 117 or something like that at your house, it's no big deal. Let's say this particular place, it's 121. The frequency, on the other hand, they have to be very careful about that. 59.9 hertz or 60.1 is no good. They have to be very precise about that. 60.01 really would be a problem. So they have to be very careful about that 60 hertz. So anyhow, pause it here, write that equation, and I'll go over it. Okay, stop share. Back in flesh. No longer a disembodied voice. Okay, if this was a quiz or something, you would find that on your formula sheet. It's there, I'm sure. And first of all, the phase angle, you were just told in the question to take that to be 0. Omega. Hertz means cycles per second. Hertz is F. So what you need for omega is omega equals 2 pi F. 2 pi times 60, 377 radians per second. The angular frequency of alternating current in North America. Europe uses 50 hertz, but in this country, the standard is 60. And we need a number to put in here. Well, don't get messed up by this effective versus peak thing. 121 volts is not the amplitude of the voltage. That's the RMS voltage. I think the way it's written on your formula sheet, it says the RMS voltage is equal to the maximum over the square root of 2. Since it's the maximum we're looking for, multiply both sides by the square root of 2. It's not a good equal sign. That looks better. So the 121 volts times the square root of 2 is 171. So put all the pieces together, put that in for that, put this in for that, and the voltage as a function of time. In other words, well, not every oscilloscope would go all the way up to 171 volts. A lot of them wouldn't, but if you hooked up an oscilloscope to that outlet so that you had a graph of the voltage in there, what's the equation of the graph you would see? And we were using sine, weren't we? Hold on. I'm working off of an outdated version of my notes here. Wait a second. Yeah, I've changed textbooks a few times over the years with this course. And, you know, sine, cosine, the only difference is the phase angle. So I should have been saying sine rather than cosine to make it match that. I don't know why I didn't. I'm just kind of hesitating, trying to decide if I did that for some reason that's deliberate, but no, I think that was just. I think that was just me messing up. So back to the blackboard. It's a quick fix. Now let's see. Back to the notes. Okay, so that's sort of a general introduction to what's going on with an alternating current. Let's talk specifically about what happens when AC goes through a resistor or a capacitor or an inductor. Let's take them one at a time. For a resistor, it's a pretty quick story. Maybe I should mention my notation I've been using here. I'm using lowercase letters for things that change with time. Little v and little I are functions of time. Capital V and capital I are just numbers. They're constants, okay? So for resistors, we have Ohm's law. Ohm's law is for direct current, or at least that's the way it's been presented so far. You can't necessarily assume that everything I said about direct current carries over to AC. For example, Kirchhoff's loop rule does not work with alternating, you know, with RMS currents, because AC, you know, AC effective currents are always positive. So if you follow a closed loop, how are you going to get a bunch of positive numbers to add up to zero? Okay, so the loop rule is for DC currents. And, or to put it another way, it's for instantaneous currents, because even if you have an alternating current, if you use a really, really short time interval, like say it's regular 60 hertz house current, okay? Changes back and forth 60 times every second. Well, if you look at that for maybe just a millionth of a second, there isn't any time for it to change any meaningful amount. So if you're looking at what's going on effectively at an instant, you're talking about direct current, even in an AC circuit. So Ohm's law says that the instantaneous voltage equals the instantaneous current times the resistance. So then for alternating currents, if this thing is equal to that thing all the time, then this thing is equal to that thing on average also. It's like if you have two students sitting next to each other and every week they get the same grade on their quiz, which would probably make me kind of suspicious after a while actually, but just for the sake of argument, if they somehow honestly got the same grade every week, you get to the end of the course, they're going to have the same average. And so if V is equal to IR at any and all instants, then they will be equal to each other on average. And a root mean squared is a kind of average, sort of. And so anyhow, the root mean squared voltage is equal to I times R. Ohm's law carries over from DC into AC. The other thing that I want to address for each of these items is the phase angle between the voltage and the current. And for a resistor, this is once again something that follows from Ohm's law. For the instantaneous voltage to be equal to the instantaneous current times the resistance, the volts and the amps would have to rise and fall together. Because, you know, as you work your way along the graph, if the voltage doubles, the current doubles. If the voltage goes down, the current goes down. In order for V, to, you know, if V is equal to IR now, and then later the voltage went up, but the current went down, they wouldn't still be equal to each other. So it follows from V equals IR, you know, since the one thing is just the other thing multiplied by some number, they have to rise and fall together. The phase angle between the volts and the amps is zero. When one of them peaks, the other one peaks. When one of them passes through zero, the other one passes through zero, and so on. That's for resistors. Well, now let's say instead of a resistor, you get a capacitor. And you do what your mother tried to keep you from doing when you were 3 years old. You stick something in an outlet. So you stick some capacitor into an AC outlet. And, well, as for what happens here, let's go back to what I was saying last week about RC circuits. Now, last week I was talking about direct current, okay? So in the picture on the left, which is there to remind you of what I was talking about last week, we started out with an uncharged capacitor, and then at t equals 0, the switch is closed. What happens next? Well, first of all, I say first of all, but it's the graph I put on the right for some reason. But originally, the capacitor is uncharged, and therefore the voltage between its plates is 0. Okay, another thing I was kicking around last week was how that the charge, you know, it comes from the definition of capacitance, C equals Q over V. It follows from that the charge is proportional to the voltage, or the voltage is proportional to the charge, if you'd rather look at it that way. So when there is no charge, the voltage is 0. As the capacitor charges up, the voltage between its plates increases, like I showed in the graph on the right. Well, as for the current in the circuit, that starts out as a maximum when you first close the switch and tapers off, okay? Last week it was that e to the minus x kind of a drop, you know, kind of a taper off graph. This is a little bit different shape when you're dealing with alternating currents, but it's still true that the current starts out at a maximum when you first close that switch, because at t equals 0, when you close the switch, there's no voltage across the capacitor yet. The only thing opposing the flow of current is Ohm's law. Well, as time passes, more and more charge collects on the capacitor. As more and more volts are between the plates of the capacitor, there's less and less volts across the resistor, and it follows from Ohm's law that as the voltage across the resistor goes down, the amount of current flowing goes down. Or another way to look at it is when electrons try and come out of the battery, you've got a whole bunch of other electrons in front of them on the negative plate of the capacitor. The more charge you let accumulate on that capacitor, the more pushback electrons get as they try to flow out of the battery. And so it drops off. Less and less current as you let more and more charge accumulate on the capacitor. So anyhow, as the voltage goes up, the current goes down. That was true from the DC circuits we were looking at last week, the RC circuits with direct current in them. And the same basic principle holds true if it's an alternating current instead of a steady voltage like we had in section 7. So in the graphs a little further down the screen, the ones with the sine and cosine wave on them, just like in the graphs further up the page, the current starts out at some value and then goes down, while at the same time the voltage starts out at 0 and then goes up, and then the vibrations continue from there, okay? The current continues to follow a cosine wave, the voltage continues to follow a sine wave. In a capacitor, the voltage, says it in the little box there next to the graphs, the voltage lags a quarter of a cycle behind the current. What I mean by that is that whatever happens, the current does it first and the voltage does it later. So for example, right at the beginning of each graph, right at t equals 0, the current hits a peak. It's a quarter of a cycle later when the voltage hits a peak, okay? It's to the right of 0 where the voltage hits a peak. So the current did it first, the voltage did it later. Or it's a quarter of a cycle into the graph when the current goes down through 0, but it's half a cycle into the graph where the voltage goes down through 0. Again, current did it first, voltage does it later, current leads, voltage lags by 90 degrees. That makes the phase angle 90 degrees in the equation. Now, the other thing I want to address, it's the same two questions for capacitors that I had for resistors. What's the phase angle and what determines how many amps flows when you apply a given number of volts? Some relationship that'll play the role of Ohm's law. Well, we have this thing called capacitive reactance, which is measured in ohms, just like resistance is. And you've got over there at the bottom left corner of the page, you've got voltage equals I times XC. That does for a capacitor what Ohm's law does for a resistor. It's volts equals amps times ohms again. The difference is that in a resistor, the number of ohms is just a fixed property. As long as you don't overheat it or something like that, a 500 ohm resistor is a 500 ohm resistor, end of story. Reactance, on the other hand, is not a fixed number. It varies with the frequency, okay? X equals 1 over omega C. Each of these devices opposes the flow of current in its own way. With a resistor, what opposes the flow of current is that the surrounding material gets in the way, okay? As the electrons try to move through any kind of a resistor, a wire or anything else, the electrons keep running into the surrounding atoms and they lose energy in the collisions. So to kind of simplify the whole thing down, the surrounding material gets in the way of the electrons trying to move through it. That's what resistance is. In the case of a capacitor, what opposes the flow of current is electrostatic repulsion. What I was just talking about a minute ago, that if you've got a battery, for example, or any other source of voltage, and there's a capacitor in the circuit, when the electrons leave the battery, they get pushed back from the electrons that are in front of them in the capacitor. And the more electrons, well, I shouldn't just say electrons, because it works the same way with positive charge on the other side of the capacitor also. The more charge you have in the capacitor, the more it pushes back against additional charge trying to flow in, because like charges repel. And so that's where capacitive reactance comes from. It's an electrostatic effect, basically. So why do we have an inverse relationship with the capacitance? Because if you've got more microfarads, there's more room in the capacitor for charge, and so it's easier to fit more in there. It doesn't push back as hard against additional charge trying to flow in during that part of the cycle where the capacitor is charging up. As for the frequency, you've got an inverse relationship with the frequency there also. And what the deal is with that is that if you've got a really low frequency, you know, it's a long time before the current turns around and flows the other way. So some charge flows into the capacitor, some more charge flows into the capacitor, some more charge. It gets pretty charged up before it's finally time for things to turn around and flow back the other way again. And with a high frequency, it's like a little bit of charge flows in, okay, time's up, back you go. So over the course of an entire cycle, the average charge in the capacitor is higher when you have a lower frequency, because the capacitor charges for a longer time. More charge in the capacitor equals more repulsion pushing back against the current trying to flow into it. And that's why you have an inverse relationship between X and omega. So capacitive reactance, measured in ohms like resistance is, but it's a completely different effect. Comes from a different physical phenomenon. It behaves differently because it's a function of frequency. And the top of the next page says in a very concise 3 lines what I just managed to stretch out to about 5 minutes explaining it to you. But, well, notes are supposed to be brief and to the point. If I ever get long-winded, you can just fast forward, I suppose. So here's a couple of problems for you to work on. Find the RMS current if you stick a 6 microfarad capacitor in a household plug, where we're going to assume, if I don't say anything to the contrary, assume you're not in England, and that house current means 60 hertz, 120 volts. So what you're going to have to do is use these equations, which are right at the top of the screen right now. From the frequency and the capacitance, you can calculate the reactance. Once you know how many ohms, that together with the number of volts will tell you the amps from the equation on the left at the top of your screen. And then just to kind of illustrate how that frequency has an effect when it's reactance rather than resistance, because again, frequency is irrelevant if you're talking about resistance. But just to show you how it changes, just run through it again with 600 hertz. XC 1 over omega C, which equals actually, I already did an example once where you calculate omega for 60 hertz house current. It's 377 radians per second. So if this wasn't already sitting here for us to look at, you'd have to calculate 2 pi f. But I suppose, since it's right there anyhow, I might as well go ahead and just stick in 377 omega. And the capacitance, six times 10 to the negative 6. Converting microfarads to farads. 442 ohms. Once you know that, V equals I times XC implies I equals V over X. So we've got 120 volts, we've got 442 ohms, 0.271 of an amp. All there is to number 3 is moving decimal points. So being basically a lazy kind of person sometimes, what have I got here? How do you feel about blue? In number 3, instead of 60 hertz, we've got 600 hertz, which makes this bigger, which makes this smaller. 44.2 ohms instead of 442. If the decimal point is there, with a smaller denominator, you get a bigger overall value, and it's 2.71 instead of 0.271. So number 3, it's just 10 times the frequency, gives you 1/10 of the reactance, and it's all just moving decimal points compared to number 2. Meanwhile, back in the handout, what about an inductor? An inductor, again, is a coil, which is inducing a voltage in itself. So that's where the reactance comes from in the case of an inductor, okay? Again, from the beginning of the story, resistors oppose the flow of current by the surrounding material getting in the way of the current trying to move through it. Capacitors oppose the flow of current because the charge already in the capacitor repels additional charge trying to flow in during that part of the cycle where the current is building up. And then once you've established the amplitude during that part of the cycle, the pattern just continues on from there. In the case of an inductor, it's a magnetic effect. Capacitors are involved in an electrical effect. Inductors, it's a magnetic effect. It's the coil's self-induced voltage, which pushes back against a current trying to flow through it, okay? As the current tries to build up during that part of the cycle where it builds up, the self-induced voltage tries to hold it down. Faraday's law says the more rapidly things change, the larger the self-induced voltage, okay? The EMF is proportional to the rate of change. At a high frequency, things change more rapidly than at a low frequency. And so the capacitor or the inductive reactance is proportional to omega, as opposed to, with capacitors, it was proportional to 1 over omega. The self-induced voltage is also proportional to L. I'd have to scroll way back up, maybe I won't try, but at the end of, I think it was the end of section 6, the self-induced voltage equaled L times delta I. Actually, I think it was minus L times delta I over delta T. So, for example, twice as big for L means twice as many volts induced. And the induced voltage is what is opposing the flow of current. So more inductance, more ohms, bigger frequency, more ohms. And so that's kind of what's going on with inductive reactance. As for the phase difference, well, the quickest way to explain this is just to say, consider the little LC circuit that I sketched here in the middle of what's in front of you. If you apply the loop rule, and I'm applying it to instantaneous voltages here, that does obey the loop rule because those are essentially DC voltages. So the voltage across, according to Kirchhoff's loop rule, the voltage across the capacitor plus the voltage across the inductor has to add up to 0. In other words, the one is the negative of the other. So back up here in a capacitor, if the voltage, or if the current was a cosine, the voltage was a sine. If the voltage in the coil is going to be the negative of this, the minus sign turns the graph upside down. So you've got a negative sign instead of a positive sine wave for the voltage. So this time, the voltage leads and the current lags. Okay, right, did I say that backwards? No, I didn't. The voltage starts out. Let's look at it this way. Hold on. I just confused myself. The voltage leads. I'm going to pause this. I think I messed up the handout. I must have pasted, whenever the last time I revised that was, I don't think it was too long ago, but I don't remember exactly. But I think it would make more sense if those graphs for the inductor looked like this. Because what I had just finished saying was that we had a graph for a capacitor where this was the current, same thing that I drew here, and for the capacitor you had a sine wave that would be positive here and negative there, and then I explained how that, well, with an inductor it should be the same thing flipped upside down. That would look like this, and that means that in the inductor, voltage leads, current lags. So, for example, the voltage starts out going down through 0. A quarter of a cycle later, the current goes down through 0. Voltage did it first. Current did it quarter cycle later. A quarter of a cycle in, the voltage bottoms out. The current half a cycle in, the current bottoms out. So again, current does it a quarter of a cycle later than the voltage does. Voltage leads, current lags. And the pictures that you were looking at a minute ago in the handout were not correct. I apparently pasted the wrong diagram in the wrong place or something. I should fix that before I have those duplicated. And so maybe you'll get a hard copy that actually looks the way it's supposed to, if you're lucky. But this is what that should have looked like. So I'm pretty sure, without going back and looking at that thing again, I'm pretty sure the next thing it talks about is Eli the Iceman. For those of you who don't know what an Iceman is, once upon a time, long, long ago, people did not have refrigerators. They had ice boxes. And guys would go out on the lakes in the middle of winter with great big saws and sleds pulled by big teams of horses, and they'd cut ice off the lakes. And they'd take it into town and they put it in big warehouses where it was stored under like 4 feet of straw. And they used the ice all winter long. And actually, people who lived in northern climates would sell ice to people who lived in the south. They just load up trains full of ice and sell it. So anyhow, what you had in your house, and they still use the same technology today when you go camping, you know, unless you've got one of these big campers that's got an air conditioner and all of that in it. If you're just your basic garden variety tent camper, you've got your little cooler, and every day you have to go buy ice to put in the cooler to keep your cold cuts and beverages and whatever you got in there cold. And that's what people used to do in their houses, you know, in the year 1900. And this guy would come around every few days and sell you a big block of ice. And yeah, that has really nothing to do with the physics at all, but maybe you got tired of listening to physics for a minute. Anyhow, Eli the Iceman. L for an inductor, C for a capacitor, E for voltage, as in EMF, because if we tried to use the letter V, it wouldn't come out nearly as nice. So E for the voltage, I for current. In an inductor, the voltage comes first, the current is on the end, voltage leads, current lags. In a capacitor, the other way around, current leads, voltage lags. So it's one of those little tricks, kind of like, you know, when you take music class, every good boy does fine, how you remember the notes on the music, you know, the sheet music. Or if you're talking about the colors of, no, that's still coming up later. Eli the Iceman has a friend. Just down the street from Eli the Iceman lives this guy named Roy G. Biv, but we'll get to him a little later in the course when I talk about electromagnetic waves. Anyhow, voltage leads, current lags, or the other way around, depending on what you're talking about. Let's see what's next in my script. Okay, to help remember this, Eli the Iceman. Yep, explains it all. And so now there is a problem for your problem-solving enjoyment. Let's see, gives the frequency, gives the resistance. Yeah, that's a good question. You think about that. And when you think about that, I'm going to erase this over here. And when you unpause it, I'll go over it. Okay. Part A. If you have 250 ohms at a certain frequency, you've got 250 ohms at every other frequency. Resistance is not a function of frequency. There are other factors that can affect resistance, like the temperature of the resistor, but assuming you don't overheat the thing, still 250 ohms. Some people just walked by. If they looked in here, they probably think I'm crazy talking to an empty room, but can't be helped. With a capacitor, it's an inverse relationship. C equals 1 over omega C, where omega is just the frequency in radians per second instead of cycles per second. Omega equals 2 pi f. So it's an inverse proportion between the number of ohms and the frequency. So if you double the frequency, that's going to give you half the ohms. So the 250 ohm resistor in part A is still 250 ohms, but there is no particular amount of ohms that goes with a certain capacitor that involves the frequency as much as the capacitance, and this would now be 125. For a coil, an inductor, it's the other way around. Since XL is equal to omega times L, double the frequency, double the number of ohms. So $500. Awkward pause while I get back to this. Okay, so I've talked about what happens if you put an alternating current through a resistor or a capacitor or an inductor. What if you make a series circuit that contains all three? Well, by the way, you can make parallel circuits, but there's only so much time in the course to cover stuff, so we're going to just cover series circuits and leave it at that. Parallel circuits are a variation on some of the same ideas, but that's, I guess, about all I'll say of that. So you've got the graphs here. Current is a function of time. That would be the same everywhere. Current is the same throughout a series circuit because, you know, every time an electron flows out of the resistor, it's got nowhere to go except into whatever's next, the coil or whatever. So you have to have the same current at any, you know, you have to have the same number of amps all along a series circuit. So all we need is one graph for that. The voltages vary because of the phase differences. Okay, Eli the Iceman. So for the resistor, second graph from the top, that rises and falls along with the current. For the capacitor, the voltage lags. So for example, right at the beginning of the graph, the current is going up through zero. The voltage in the capacitor goes up through zero a quarter of a cycle later, so the voltage is lagging. For the inductor, the voltage starts out at a peak, a quarter of a cycle later, the current hits a peak, and so voltage leads, current lags. Voltage peaked first, current peaked a quarter of a cycle after that. Because of these phase differences, the way voltages add together is not as simple as it would be with direct current. Okay, well, let's save the resistor for last, and just for the moment think about a capacitor and an inductor in series. If you have two things in series with direct current, if there's 5 volts across one and 4 volts across the other, then the total voltage across both of them is going to be 9 volts. Okay. But if you're talking AC voltages, if you refer back up to those graphs, notice that whenever the voltage on the capacitor is positive, the voltage on across the inductor is negative. And whenever the capacitor is negative, the inductor is positive. So it's not two steady voltages you're adding together, it's two vibrations, two waves, using the word rather loosely. Whenever the one is positive, the other one's negative, you're going to end up subtracting their amplitudes rather than adding them. So like it says near the, not quite, but near the bottom of the page here, if VC is 5 and VL is 4, the total of the two is 1 volt, not 9, because the voltages are always negatives of each other, okay? Well, then if you add the resistor into the mix, the resistor is not quite in phase or not quite out of phase with either one. It's somewhere in between, which makes things a little more complicated. If you work through the details, what you end up with is that equation near the bottom of your screen, that the total voltage across all three of them, what would be read, I drew this all in the diagram there, the little circles with V's in them, those are supposed to be voltmeters, okay? So the diagram supposedly shows a meter reading the voltage across the capacitor. I called that voltage VC, and another meter reading the voltage across the inductor, and I called that one VL, and a meter on the resistor. And then VT, that's a meter that reads the voltage across the entire group. And the way that that voltage across the entire group relates to the three individual voltages is that formula with the square root in it there, which looks reminiscent of the Pythagorean theorem, okay? Now, voltage is actually a scalar. It doesn't really have a direction, but it behaves like it does. And so this so-called phasor diagram, you can just think of that as a diagram suggested by the formula. Voltage doesn't really have a direction, as in over here we have 5 volts toward the north, and over here it's 3 volts toward the east, or anything like that. Voltage is just simply how much of a difference in potential is there between the one end of the resistor and the other. But see, the directions on the diagram aren't real directions like north or east. Rather, they correspond to phase. That's why it's called a phasor diagram. Something that points to the right that represents a vibration that has a phase angle of 0 degrees. Something that points up, that's a phase angle of 90 degrees. Something that points down, well, down represents a phase angle of negative 90 degrees, where positive and negative depend on what leads and what lags. Okay, if the voltage leads, that's a positive phase angle. If the voltage lags, that's a negative phase angle. So we have a problem for you to do. And it basically refers back to that diagram that's, here, tell you what, I'll put it right there. Put it right at the top of the screen so you'd know which one I was talking about when I said the diagram that's right at the top of the screen. So the problem number 5 that's in the middle of your screen tells you what the 3 individual voltages are: the capacitor, the inductor, and the resistor. And based on those, you're supposed to tell me the voltage across the entire group, V total, VT. And once again, you should pause that and work on it while I'm erasing a spot on the blackboard to write out the solution. Number 5. Okay, it's a good question where I put the answer to number 5. 1. There it is. Sure, I'm a very organized person. Okay, number 5. This is just dropping numbers. This is just dropping numbers into the formula that's in front of you and punching it up. The voltage across the entire group is the square root of the voltage across the resistor and VL minus VC. It says there's 20 across the resistor, 40 across the inductor, and just because for the heck of it, I felt like making the answer come out an even number. The capacitor is not an even number, so that the answer would come out even. 62.36. Now, if these were DC voltages, you would just add them up to get the total. That plus that would be 122.36, but that's how to do the question wrong. If you're interested in doing the question right, you fill it in this formula here, you square that, you subtract and square. By the way, maybe I should remind somebody that when you square a negative number, the minus sign goes away, okay? So once in a while, somebody ends up subtracting in a case like this because they think when they square, you know, because 40 minus 62 gives you something negative, but the minus sign goes away when you square it, and you end up adding, not subtracting. So this is going to be 20 squared is 400 plus 22.36 squared is 500 Square root of 900 is 30 volts. Which is actually smaller than 2 out of the 3 individual voltages. But, you know, it's the phase differences that make the voltages cancel. Not completely, but to some extent. Okay, I should make some effort to keep my pages in order here. 18.5. Share screen. I kind of like being able to point at things with a pencil, have a hard copy in front of the camera, but I thought I had brought one with me and I didn't. But the good news is you get a nice clear copy this way. When I point a camera at a hard copy, it doesn't always come out so clear. Okay, so that takes care of number 5. Now we want an Ohm's law relationship for the circuit, Ohm's law-like relationship for the circuit as a whole. And that involves a quantity called impedance, which once again is a thing with a square root in it. So there's another little right triangle type diagram that's suggested by the formula. But what's lurking behind all the formulas is resistance is a type of impedance, and the 2 different reactances are types of impedance. Impedance is everything that in any way impedes the flow of current, okay? So the total number of ohms from resistance, capacitive reactance, and inductive reactance put together is Z. Scroll down. I guess one's an example. That's my cue to do it for you as something you can imitate. So I'm going to run through number 6 right now, although feel free to try it yourself if you think you've got it figured out. But for anybody who needs sort of something to imitate when you do number 7, well, number 7 isn't exactly like number 6, but it's a lot like it. To calculate both reactances, I need to know omega. So maybe I should just get that out of the way right at the beginning. Omega 2 pi f. .500 hertz for f. Remember, f is cycles per second, omega is radians per second. So hertz is f. 3142. Maybe I should tell you where I'm going with this. To get the current, it's going to be amps equals volts divided by ohms. Well, the question told us how many volts. It's written on the diagram there. Most of the work is figuring out how many ohms. So I have to figure out how many ohms for the capacitor, how many ohms for the inductor, and then stick all that together to find the impedance, which is the total number of ohms for the entire group. Finally, amps equals volts divided by that many ohms. Okay, so that's the plan of attack here. XL equals omega L. That's the 3142 times 0.0095 of a Henry. And you probably could get away with carrying less decimal places, but I like to carry an extra decimal place and then round off when I get to the end. 29.85. Reactance is measured in ohms. .5 microfarads. Micro means 10 to the negative 6. I didn't leave myself much room for the answer, but it's 70.73. I guess that fits. Now that I know all that, and I've known the resistance all along, Z, impedance, I took a course in statistical mechanics when I was a junior from a guy who crossed his Z's like that, and it seems to have stuck because that was a long time ago. Anyway, we've got 50 ohms. That's R. And then we need XL minus XC. So the 29.85 minus 70.73. Subtract first, then square. You can't interchange the order, it won't work. Basically 64.6, 64.58 ohms. $20 volts divided by the 64.6 really would be close enough. 0.310. Incidentally, this is not only sort of a pattern you can imitate doing the next problem in the notes here, but you'll have to do a very similar calculation in the lab that goes with this. You're gonna make an AC circuit and predict what some of the measurements would be, and then you go in and actually measure it and see if they match. And you're going to have to pretty much do exactly what I've just been writing out here with that. Well, I've got to make a little room to write over here for part B. Or after the phase angle. So this side is the resistance, R. That's a right angle there. This side is XL minus XC. So 29.85 minus 70.73 is negative. In fact, it comes out negative. I mean, I just started out by drawing sort of a generic triangle, but now that I see that's negative, that tells me it actually looks like this. That you've got 50 here and 40 point, about 40.9, 40.88 pointing downward. Okay, you've got it's going to be a negative phase angle. So a little bit of trigonometry. We know the opposite and adjacent sides of this triangle. Opposite over adjacent is the tangent. Negative 40.88 over 50. Well, this is not the number we're interested in. This is just sort of a step along the way. 0.8176 is not the angle, it's the tangent of the angle. To get the angle itself, that's the inverse tangent, or the notation on most calculators would simply be second function tangent. So back to this. Number 7, you try that. And I'll unshare this. Kind of just the same thing that's still over there. XC 1 over omega C. Omega is 2 pi f. Don't happen to remember from that earlier example that 2 pi times 60 is 377. You have to calculate 2 pi times 60 to get omega. C is 5 times 10 to the -6, 5 microfarads. Why is that fuzzy? Stop doing that. Okay, I guess it feels better now. 5 microfarads. $530. Excel. Yeah, I get questions about this sometimes. What am I don't know. What do I use for that? There is no it's the inductor. There is no inductor. Therefore, the inductor that isn't there does not do anything to impede the flow of current. It would have to be there to impede the flow of current in any way. So you get 0. There is no inductor, so XL is 0. The impedance then, R squared plus XL minus XC squared. Resistance is 300. $609.5. Well, let's see. That's not the answer yet. Why did I put a box around that? Current .197. As for the phase angle, would be the inverse tangent of, maybe I should draw the little triangle again. We've got 300 for the resistance. Negative, well, in other words, 530 downward. XL minus XC is 530 downward. And I guess I'll put the minus sign on it. Even though it's kind of redundant when I draw it that way. Inverse tangent of opposite over adjacent. Negative 65.5. No, 60.5, not 65 degrees. And then the last thing in this unit is resonance. Impedance is a function of frequency, okay? Impedance, it's written there about 2/3 of the way down what's in front of you. Impedance is equal to R squared plus XL minus XC squared. Resistance never changes as you change the frequency, but XL and XC are both functions of the frequency, therefore the impedance is the function of the frequency. So if you have one of these RLC series circuits and you start dialing up different frequencies, maybe we've got half a dozen of them here in the lab of the, function generators where you just turn a dial and you get different frequencies that way. If you go to very low frequencies don't want to go through a capacitor, okay? It's, well, the lowest frequency of all would be 0. 0 means steady current, steady direct current. And to DC, a capacitor is a broken wire, okay? An alternating current can exist in a circuit with a capacitor because you don't actually have to have a complete circuit. With direct current, electrons have to be able to flow out of one terminal of the battery, go around the loop and return back into the other terminal of the battery and go around and around over and over again if you leave it turned on long enough. But with an alternating current, all the electrons ever do is jiggle back and forth. So they don't actually have to have any place they can go. So even though the two sides of a capacitor don't touch each other, electrons can flow into the negative plate and then back out of the negative plate and into the negative plate and back out of the negative plate. So an alternating current can exist in a circuit with a capacitor because you just keep charging it and discharging it over and over again. But to a frequency of 0, a capacitor is a broken wire. And so the current is 0 when the frequency is 0. On the high end, it doesn't want to go through the coil, okay? What opposes current flowing through a coil is the self-induced EMF. The self-induced EMF depends on the rate that the magnetic flux through it is changing, which depends on the rate the current producing that flux is changing. And so the higher the frequency, the bigger the back EMF, and as the frequency gets very high, the amount of opposition gets very high, and so an alternating current doesn't want to go through a coil on the high end. Somewhere in between, there's sort of a Goldilocks kind of thing going on. It's like this frequency is too high and this frequency is too low, but this frequency is just right. And that just right frequency, if you look at the formula for impedance, the one with the square root of R squared plus XL minus XC, if those XL and XC terms cancel each other, then all you're left with is the resistance. And if the resistance of the circuit happens to be pretty small, 5 or 10 ohms or something like that, you could get quite a large current at that particular frequency. So if XL, like I've got this all written out in front of you there, if XL equals XC, well, XL is equal to omega L, XC is equal to omega C. You rearrange things a little bit, and it turns out that the frequency where you get that maximum response is equal to 1 over the square root of LC, which hopefully seems just a little bit familiar because, where are we here? If you go back up to the end of the previous unit, here we are at the end of section 7, the frequency of an LC circuit is 1 over the square root of LC. That's the same thing we got down here, if I don't overshoot. There it is. This is an effect that's called resonance. Resonance occurs in many different types of vibrating systems. If you've got some sort of driven oscillations, it'll come up again a couple of weeks from now when we're talking about standing waves. But in general, if you drive something at the frequency that it would, its natural frequency of vibration, okay? If you have a pendulum, like a kid on a swing at a playground is basically a pendulum. If the frequency that the pendulum swings with is one swing every 2 seconds, then if you push the swing once every 2 seconds, making the frequency of your driving force equal the frequency that the swing swings with. If you drive it at its resonant frequency, a large amplitude builds up. Okay, the swing goes back and forth real good after you've pushed it a number of times. If you were to be foolish enough to try and push the swing at some other frequency, it wouldn't work very well at all. So just like pushing on a pendulum, the pendulum resonates if you drive it at its natural frequency. It's the same with this RLC circuit. Adding resistance to the LC circuit is basically like adding friction to a mechanical oscillator. It doesn't change its frequency. It just means that the thing will stop vibrating before very long if you've got some friction there to take away the energy. But anyhow, if you drive this circuit at that frequency, you get a large amplitude response. If you try to drive it at other frequencies, it doesn't work so well. There are a number of applications of this kind of thing. The one that's coming up in this last example is the tuner for a radio. Radio basically, in a way, is kind of like a transformer. We looked at transformers a week or two ago, and there were two circuits. You had the primary circuit and the secondary circuit. You put an alternating current into the primary circuit, and it creates a changing magnetic field, which induces a voltage in the secondary circuit. Well, the same is true with radio, except instead of the primary and secondary circuits being like a fraction of an inch apart, they're miles apart. But the transmitter is like the primary circuit of a transformer, and the circuit with the antenna in your receiver is the secondary circuit. Now, being miles away from the primary, it's a very weak signal that gets induced on your antenna, and so it has to be amplified before it can drive a speaker. But and that's a long story. But the part of it that I want to get involved in right now is the fact that there is more than one radio station out there. So you don't want to turn on your radio and have like 20 different radio stations all come out of it at the same time, like being at a party where everybody is the same distance from you, so they're all talking equally loud, and you can't make a, this one over here is playing music. This one over here is talking about politics. That one over there is talking about religion. This over here, they're playing a different kind of music, and it's all there at the same time, and it would make you just want to turn the radio back off. You need to somehow single out the station you want to listen to. Well, what you do is you have a circuit in the radio similar to what I've just been talking about, and you make the resonant frequency equal the frequency of that radio station, okay? And it's designed in a way so that the peak on that graph is nice and narrow, so that the next closest stations to either side are over where the induced current would be much, much weaker. And that's how you filter out all the other stations aside from the one that you want to listen to. The tuning knob, the traditional way of doing it anyhow is with a variable capacitor, or you could use a variable inductor anyhow, or either. You could also use a variable inductor, but if you, here just a second, let me get the camera back. One way of making a variable capacitor would be, you've got your set of parallel plates, like these two sheets of paper. Well, if they're attached, let's say a corner of these plates was attached to a rod over here where I've got the pencil. And on the end of that rod is a knob. When I turn the knob, it makes the one plate, actually there's usually a whole set of plates, but if turning the knob makes the one plate kind of, I should be further back from the camera, I think. Turn the knob, it makes it rotate like that so that you adjust the amount of area between the plates. That's going to change the capacitance. There are ways to make variable inductors also. You have a lot of wire wound around here. And, you know, the signal goes in one end, and you've got like a sliding contact that moves along there, so you can change the number of turns that the current goes through. That would be one way to do it. There's even others. And so by turning the knob, you adjust the resonant frequency of your radio, kind of like the way that turning the tuning knobs on a guitar adjusts the resonant frequency of the string that you're plucking. Turning the knob on the radio adjusts the resonant frequency of the circuit in your radio. You tune the radio by adjusting the resonant frequency. You tune the guitar. That's why they call it tuning. It's the terminology carries over from music, because, you know, guitars were around first. But anyhow, you adjust the resonant frequency so that it matches the station you want to listen to. All the other stations are off, where you get a much weaker response, and that's how you filter out the one station you want to listen to. So mostly I wanted an excuse to tell you that story and give you some idea of one application of all this stuff. The problem itself is pretty straightforward. It tells you the frequency you want to have, and it tells you what you've got for an inductance, and asks what, basically it tells you 2 out of the 3 things in that formula and asks you to calculate the third one. So while you work on that, I'll erase a little section of the blackboard one more time. Omega equals 1 over the square root of LC. I want to solve for C. So I could put in the numbers and then do the algebra, but I'm going to do the algebra first and then put in the numbers. Square both sides. And then you cross multiply so that C equals 1 over omega squared L. Omega is 2 pi f. So 2 pi, the desired frequency is 1 times 10 to the 6th hertz, which incidentally is right in the middle of the AM band. AM stations give their frequency based in kilohertz. So this would be 1,000 kilohertz. And 7.96 times 10 to the negative, a little more space, 10 to the negative 6 of a Henry. And don't forget to square. I almost forgot my little 2 there. So assuming that you remember to square, it comes out 3.19 or 3.18. Don't know where I got the 9 from. Oh, because it's 10 to the negative 9, probably. That capacitance together with that inductance will give you the desired resonant frequency. And we don't get into this in this course, but there are also values that will give you a nice narrow peak for that graph so that other nearby stations don't intrude. And that pretty much takes care of section 8, which concludes our look at electricity and magnetism, actually. This is the end of what's on the second exam. What's on the third exam is stuff about waves and optics and things like that. So we'll be going off in a little bit of a different direction after this. Although we're not entirely done with it, I will occasionally mention electromagnetic waves, which is a topic related to this stuff. But for the most part, we're done with electricity and magnetism. And I'm done making this particular video.